We'll start in about 1 minute. In a few minutes, we'll start section 11.7 on the strategy for testing series. But first, we'll finish section 11.6. So we'll review a couple of things first. The definition of an absolutely convergent series. A series of a sub n terms is called absolutely convergent if the series of the absolute values of the a sub n terms is convergent. And then another definition, a series of the a sub n terms is called conditionally convergent if it is convergent but not absolutely convergent. So perhaps the most famous example of that kind is the alternating harmonic series, which is convergent, but in absolute value, we have the harmonic series, which is divergent. And then theorem 3, if a series is absolutely convergent, then it is convergent. Okay, after that, we discussed the ratio test. Let's review the ratio test. When testing the series of the a sub n terms, if the limit of the absolute value of a sub n plus 1 over a sub n as n approaches infinity is equal to a finite number less than 1, then the series is absolutely convergent, which means that it's convergent since every absolutely convergent series converges. But if the limit of the absolute value of the a sub n plus 1 divided by a sub n as n approaches infinity equals a finite number greater than 1, or if that limit is equal to infinity, then the series is divergent. And if the limit of the absolute value of a sub n plus 1 over a sub n is equal to 1, then the ratio test is inconclusive. Okay, in addition to the ratio test, we have the root test. So let's review the root test real quick. When testing the series of the a sub n terms, if the limit of the nth root of the absolute value of a sub n as n approaches infinity equals a finite number L which is less than 1, then that series is absolutely convergent and therefore convergent. But if the limit of the nth root of the absolute value of a sub n is equal to L, which is greater than 1, or if that limit is equal to infinity, then the series is divergent. And if the limit of the nth root of the absolute value of a sub n is equal to 1, then the root test is inconclusive. Okay, we got to this example last time. The directions say use the root test to test the series. The terms are 1 plus 1 over n to the n. So it seems natural to use the root test since we have this expression 1 plus 1 over n raised to the n. But when we computed this limit, we found that it's equal to 1. So it turned out that the advice to use the root test wasn't very good because the root test is inconclusive. So we have to test this series using some other method. So I may have mentioned last time what we would do. I don't remember. What do you suppose we could try since the root test is inconclusive? Well, let's take the limit of those terms from the series. If it turns out that the limit does not equal 0 or does not exist, then the test for divergence will tell us that the series diverges. So let's take the limit of 1 plus 1 over n to the n. You might have seen this limit before. Does anyone remember anything about this limit of 1 plus 1 over n to the n as n goes to infinity? Well, all of the terms are positive. So I'm going to rewrite 1 plus 1 over n as e to the natural log of 1 plus 1 over n. Then when we apply the outer exponent, we get the limit as n approaches infinity of e to the n times the natural log of 1 plus 1 over n. Yeah, this is looking more familiar. I think we've done this before this semester. So n times the natural log of 1 plus 1 over n in the exponent. That's equal to the natural log of 1 plus 1 over n divided by 1 over n. So rather than writing down e to the limit of this exponent, let's just compute the limit of the exponent. So as n goes to infinity, the numerator goes to the natural log of 1 plus 0. The natural log of 1 is 0. And the denominator, as n goes to infinity, also goes to 0. So we can apply the L'Hopital's rule maneuver on this one. Okay, the derivative of the natural log of 1 plus 1 over n is negative 1 over n squared over 1 plus 1 over n. And then in the denominator, the derivative of 1 over n is negative 1 over n squared. Okay, so this is the exponent, and when we simplify this, it becomes 1 over 1 plus 1 over n. And the limit of this is 1, so we get e to the first. So in college algebra, even though you didn't formally discuss limits, you may have learned in that course that 1 plus 1 over n to the n approaches the number e as n gets large. Okay, so since the limit does not equal 0, this series diverges by the test for divergence. Okay, let's move on to the next page. So classify the following infinite series. In other words, determine if the series converge or diverge. Any suggestions on which test to use on this one? The terms are n over the natural log of n to the n, as n ranges from 2 to infinity. Okay, let's try the root test. The root test sort of suggests itself because in the denominator we have the natural log of n to the n. So we can see what happens. Take the limit as n approaches infinity of the nth root of the absolute value of n over the natural log of n to the n. The absolute values aren't necessary because all of the terms are positive, but the nth root of the natural log of n to the n in the denominator is just the natural log of n. And the numerator is the nth root of n. Okay, what's going to happen? We have seen the limit of the natural, we have seen the limit of the nth root of n before. So the limit of the nth root of n is 1. And the limit of the natural log of n is infinity. So 1 over infinity is not really a number, but this tells us that the limit is 0. Okay, so since 0 is less than 1, the root test says that this series is convergent. All right, the next one. Any suggestions on what test to use for this series? The terms in the series are 2n factorial divided by n factorial squared. Okay, let's try the ratio test. So remember the ratio test, compute the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. Well, be careful with the arithmetic with these factorials. Once again, we don't need the absolute values, but I'll put them in. So the a sub n plus 1, that's what you get when you replace each of the n's with n plus 1. So inside this set of parentheses, we have 2 times the quantity n plus 1, which is 2n plus 2. So this will be 2n plus 2 factorial. And then in this denominator, we have n plus 1 factorial, and we're squaring that. And then we're dividing by the a sub n term, which is 2n factorial over n factorial squared. In the next step, let's omit the absolute values. And I'm going to rewrite, well, I'll wait until the next step. Let's just write 2n plus 2 factorial over n plus 1 factorial squared. And then multiply this by n factorial squared over 2n factorial. This 2n plus 2 factorial, that means the same thing as 2n plus 2 times 2n plus 1 times 2n factorial. And the n plus 1 factorial squared, well, the n plus 1 factorial means the same thing as n plus 1 times n factorial, and then we're squaring that. And then this numerator, I'll just write that here, times n factorial squared. And then that denominator, 2n factorial. Okay, so we start to see when using the ratio test, we generally expect cancellations to occur. We can see one right away. The 2n factorial from the numerator cancels with this 2n factorial from the denominator. There's another cancellation emerging here because we have n factorial squared in this one. But let's go ahead and write the next term with a couple of changes. This factor here, this binomial 2n plus 2, I'm going to write that as 2 times n plus 1 because I see a factor of n plus 1 in the denominator. So be careful with the arithmetic. Inside the parentheses, we have n plus 1 times n factorial, but that quantity is squared. So when we distribute the outer exponent, we have n plus 1 squared, and then n factorial squared. And we get a couple more cancellations from the numerator. N factorial squared cancels with n factorial squared in the denominator. And then one factor of n plus 1 is going to cancel from the numerator and denominator. All right, so we'll get 2 times 2n plus 1 after this n plus 1 factorial is canceled. And then we just have one factor of n plus 1 in the denominator. And we're about ready to compute this limit. So in the numerator, we have 4n plus 2. In the denominator, n plus 1. And we know how to compute this limit. As n approaches infinity, this limit is 4 over 1, or 4. Okay, and since 4 is greater than 1, and we're using the ratio test, that tells us that the series diverges, or is divergent. Okay, the next one. Here we have an alternating series. And so the negative and positive terms are multiplied by 2n over 5n plus 2 to the nth. So maybe the root test will work. So let's try the root test. Okay, so the limit as n approaches infinity of the nth root of the absolute value of negative 1 to the n minus 1 times 2n over 5n plus 2 to the nth. Well, the absolute values are going to, we won't need to write negative 1 to the n minus 1 after we compute the absolute value. And then the nth root of the rational expression to the n, that's going to simplify to the limit of 2n over 5n plus 2 as n approaches infinity. So what's the value of this limit? So hopefully, if not already, you can tell immediately that this limit is 2/5. Let's go ahead and go through the procedure for this kind of limit. End of the first is the term with the largest exponent in the denominator. So if you multiply that expression by 1 in the form 1 over n over 1 over n, I'll go ahead and write it. So 2n times 1 over n in the numerator And in the denominator, multiply each term by 1 over n. So in the numerator, 2n times 1 over n is 2. In the denominator, 5n times 1 over n is 5. And then plus 2 over n. And as n approaches infinity, 2 over n goes to 0. And so the limit is 2/5. All right, we're using the root test, and since that limit is less than 1, the series converges, or the series is convergent. All right, now we can start section 11.7. Uh, 11.7 is just a summary of what we've learned about series. And it gives some advice on how to determine if a series converges or diverges. So first, this statement. With practice, one can develop a sense for which test to use to show whether an infinite series converges or diverges. The authors in the textbook note that if you just go through a list every time, that can be a waste of time. So try to develop a sense for which test to use. A geometric series has one of these two forms. The terms could be in the series a times r to the n minus 1 as n goes from 1 to infinity, or just a times r to the n as n goes from 1 to infinity. Regardless, those series will converge if the common ratio is less than 1 in absolute value, and it diverges if the absolute value of the common ratio is greater than or equal to 1. If there is a function f that is continuous, positive, and decreasing on the interval from 1 to infinity, such that f of n is equal to a sub n, then the integral test can be used to test the infinite series of the a sub n terms, provided that the improper integral of f of x dx from 1 to infinity can be evaluated. So if the improper integral converges, then so does the infinite series. And if the improper integral diverges, then so does the infinite series. A series of this form, the terms are 1 over n to the p as n goes from 1 to infinity. This is called the p-series, and it converges if the exponent p is greater than 1, and it diverges if p is less than or equal to 1. If a series has a form similar to a p-series or a geometric series, then the comparison test or the limit comparison test might be able to be used. And then the test for divergence for a series with a sub n terms, if the limit of a sub n as n approaches infinity does not equal 0 or does not exist, then the series diverges according to the test for divergence. Okay, for alternating series, if the b sub n terms decrease and if the limit of the b sub n terms is 0, then the series converges according to the alternating series test. If a series has factorials and or a constant raised to the nth power, then the ratio test might work. And then if it turns out that a sub n is equal to b sub n to the n, then the root test might be the test to use. The very last sheet on the lecture notes just gives an overview of the different tests. We're not going to read through them. I'll just note the ratio test is there, the root test, alternating series test, the comparison test. However, I think I will read the limit comparison test, just so we don't confuse it with the limits that we compute using the ratio test and the root test. So the limit comparison test says, suppose you have two series, one with a sub n terms and the other with b sub n terms that are positive terms. If the limit of a sub n over b sub n is equal to c, where c is a positive finite number, then either both series converge or both diverge. Okay, so let's start looking at more examples. So classify the following infinite series. The terms in this series are n to the second minus 1 over n to the third plus 1. And n begins at 1. So is there, in your experience so far, is there a particular test that comes to mind? The first thing that comes to my mind is when I look at the term with the largest exponent in the numerator and compare it with the term with the largest exponent in the denominator and simplify it, n to the second over n to the third is 1 over n. So I'm going to try the limit comparison test with the harmonic series, where the terms are 1 over n. So what do we know about this series? Okay, this series is the harmonic series, which is divergent. And we reviewed the limit comparison test a minute ago. So if I compute the limit of n squared minus 1 over n to the third plus 1 over 1 over n, and if that limit is equal to a positive number, then since this series converges, or diverges, I mean, then this one will also diverge. Okay, so the limit as n approaches infinity the term from one of the sequences, or one of the series, n squared minus 1 over n to the third plus 1, divided by the nth term from the other series. And then we'll do algebra and arithmetic. So this will become n squared minus 1 over n to the third plus 1 times n over 1. So in the numerator, the limit of the numerator n to the third minus n, and the denominator n to the third plus 1. Hey, what does that limit equal? So with practice, you'll know immediately what that limit is. But I suppose if it's not obvious, let's go through the procedure. This is a rational expression. The term with the largest exponent in the denominator is n to the third. So we'll multiply that rational expression by 1 in the form 1 over n to the third over 1 over n to the third. And then after that, compute the limit. Okay, so we're going to multiply n to the third minus n by 1 over n to the third. And we'll multiply n to the third plus 1 by 1 over n to the third. We're not breaking any rules, we're just multiplying by 1. All right, so n to the third times 1 over n to the third is 1. And then minus n times 1 over n to the third is 1 over n to the second. In the denominator, n to the third times 1 over n to the third is 1. And then plus 1 times 1 over n to the third is plus 1 over n to the third. And as n approaches infinity, the 1 over n to the second goes to 0, and 1 over n to the third goes to 0, so the limit is equal to 1. Okay, so in the limit comparison test, if the limit is a positive finite number, then both series do the same thing. So since the series that we chose to compare it with is divergent, the given series diverges also. So this series this is divergent. Okay, the next example. The sum, the terms are e to the n divided by n to the second, and n begins at 1. So what do you think? Well, in the numerator, e to the n, that grows a lot faster than the denominator, n to the second. The numerator is exponential and the denominator is a polynomial. So exponential functions with a positive base, like e, grow a lot faster than polynomials. And all of the terms are positive in both the numerator and denominator. So my thought is that this must diverge. So we could try the divergence test. Test for divergence. Well, we get infinity over infinity. So L'Hopital's rule can be used. The derivative of e to the n with respect to n is just e to the n. And the derivative of n to the second with respect to n is 2n. And then this limit is also infinity over infinity, but we can use L'Hopital's rule again. And then we get the limit as n approaches infinity. The derivative of e to the n with respect to n is e to the n. The derivative of 2n with respect to n is 2. And this limit is obviously infinite. So since the limit does not exist, this series diverges by the test for divergence. Okay, the next one. The series, the terms are n to the second times e to the negative n to the third. N begins at 1. Any ideas on this one? One of the things that stands out, we have e to the negative n to the third, and the derivative of negative n to the third with respect to n is negative 3n to the second. And we see an n to the second. And these terms, n to the second times e to the negative n to the third, that means the same thing as n to the second over e to the positive n to the third. So these terms are positive for n greater than or equal to 1. And the denominator gets bigger faster than the numerator, so as n increases, the terms decrease. So I'm thinking that the integral test will work for this one. All right, so the integral test, the improper integral from 1 to infinity of x to the second times e to the negative x to the third. So if we assign u to be negative x to the third, then du is negative 3x to the second dx. We have x to the second dx. So if we multiply both sides of this by negative 1/3, we get negative 1/3 du equals x squared dx. All right, so we can transform this improper integral, replace x squared dx with negative 1/3 du, and replace e to the negative x to the third with e to the u. Okay, I'll put the negative 1/3 factor on the outside, and then e to the u du. And then we have to change these limits. When x is positive 1, u is negative 1 to the third, or negative 1. And when x goes to positive infinity, u goes to negative infinity. Well, we can rewrite this. The upper limit is negative infinity, so that's in the negative direction compared to where negative 1 is. We can use a property of integrals. We can reverse the limits if we take the negative of negative 1/3. So we can rewrite this as positive 1/3. And then from negative infinity to negative 1, e to the u du. So I suppose we should write it as a limit. 1/3 times the limit as b approaches negative infinity of the integral from b to negative 1, e to the u du. And we get 1/3 times the limit as b approaches negative infinity. An antiderivative of e to the u with respect to u is e to the u. We evaluate this from b to negative 1. So we're almost done. So the upper u value is negative 1, so we have e to the negative 1, and then minus e to the b. Well, as b approaches negative infinity, e to the b approaches 0. And so the limit is just 1/3e, which is a finite number. So since the improper integral converges, the series converges. So I think that will be the last thing I write, since that improper integral that we wrote down to start with the series also converges. Okay, we're out of time. Go ahead and sign in.